our understanding of the universe is a house of cards, built high upon a scaffold of pre-existing theories and tentative, one-off results. And so, most experiments in modern theoretical cosmology are not as they were in the early days of physics. They are not voyages of blind discovery, but rather finely tuned confirmations of predictions already made, of results already hinted. The Higgs boson was first predicted in 1964 and finally confirmed in 2013, just as expected. But what scientists really hope for are surprises. A result that topples the house of cards and builds a new one in its place, or totally cements the linkages and proves the theories once and for all. And so, in early 2021, in a laboratory near Chicago, 200 virtually assembled scientists shed a gasp of excitement at just such a result. The experiment and analysis was the culmination of more than 60 years' work involving physicists from 35 institutions in 7 countries worldwide. And yet, until an envelope was opened in Batavia, Illinois, and a secretive key typed into a computer, not one of them really knew what they had accomplished. This elaborate cloak-and-dagger approach to experimental physics, perhaps more suited to a star-studded film festival, was necessary to avoid any one of the hundreds of collaborators inadvertently biasing their findings towards the desired outcome. This latest experiment at Fermilab was concerned with the behavior of muons. These exotic particles are the heavier cousins of the electrons and exist only for a couple of microseconds before decaying into something else. Like an electron, a muon has electric charge and behaves like a spinning magnet. But that spin wobbles when muons move through a magnetic field. So, using the incredibly complex mathematical tools of quantum mechanics and the so-called standard model of particle physics, scientists have predicted exactly how much the muons should wobble. This theoretical prediction represents the sum of what we think we know about how the universe works. And the elaborate experiment at Fermilab was designed to test this theory, to find out if we are right. To do this, researchers spent 4 years installing and calibrating a huge, C-shaped magnet, some 15 meters in diameter, with an impeccably uniform magnetic field. For more than a year, they sped muons around the magnet and measured their wobble. And sitting at the controls of this machine, waiting for the beam to fire, our researchers would have had plenty of time to contemplate the theoretical house of cards on which their predictions were built. All matter in the universe, from the muons inside the magnet to the researchers themselves, is subject to 4 fundamental, irreducible forces. Gravity keeps the scientist pinned to the seat of her chair, keeps the huge magnet stuck to the surface of the Earth, and keeps the Earth in orbit around the Sun. Electromagnetism provides the invisible pull within the gigantic magnet, but it does more than that. It is responsible for the electric currents that flow through the equipment's controls, and for the electrical impulses that spark through the scientist's body to keep her heart beating and her neurons firing. Shrinking down further to the scale of atoms themselves, the strong nuclear force grips the particles together in every atomic nucleus, holding them fast despite the repulsion of their like charges. Without this force, not a single atom in her body, the room, or the entire universe could exist. They would simply fly apart in a cloud of unconnected quarks. And yet, in a few thousand atoms inside the scientist's body, the weak nuclear force is driving such elemental destruction. The 4th fundamental force is the agent of radioactive decay, which sees atomic nuclei, like the potassium-40 inside our cells, cracked open and transformed. Together, the actions of the 4 fundamental forces, gravity, electromagnetism, and the strong and weak nuclear forces, are enough to describe every single phenomenon in the universe today. Except for, it seems, the wobble of muons. The revelation unlocked with the opening of Fermilab's envelope was that the intricate predictions, built on these 4 forces for the muons, were not, in fact, correct. Muons wobble more than they should, and the results showed with unprecedented precision that there is likely to be something else at play, a 5th force, as yet undiscovered. There is still much work to be done to understand the significance of this curious muon wobble, but it gives us cause to re-examine what we think we know about the 4 fundamental forces that we are aware of. Our understanding of them, too, the result of centuries of scientific revelation. Why are they fundamental to the universe? And are they really as distinct as we think? How did the directionless quantum foam at the beginning of our universe give birth to these fundamental natural laws? Extending our house of cards back to the very birth of the cosmos, we find that things looked very different for a brief moment of grand unification. The existence of invisible forces at play in our universe has been recognized for thousands of years, and mankind has strived to understand and harness them for almost as long. Lodestones, pieces of naturally magnetic rock, were treasured and used for divination by the Chinese since the 2nd century. Ancient Egyptians were wary of shocks from electric fish, and early philosophers experimented with static electricity with rods of amber rubbed on cat's fur. But these strange phenomena graduated from mere curiosities in the 17th and 18th centuries, as the scientific revolution forced them to yield their secrets. They became the subject of rigorous study by scholars and statesmen alike. Founding father Benjamin Franklin reputedly sold all his possessions in order to fund his research into electricity. It is ironic, therefore, that his most famous experiment required little more than a kite, a key, and a thunderstorm to prove that lightning was electric in nature. The summer of 1864 was a hot, dry swelter. It had barely rained since April, and in the offices of King's College London, the air hung heavily in the dim, wood-panelled rooms. Desperate for some relief from the baking heat, James Clerk Maxwell staggered to the window and heaved the sash open, letting in the clamour of the streets below. The air had a sharp and slightly sweet smell to it, one that Maxwell knew heralded a coming lightning storm, and which we today would recognise as the distinct smell of ozone. He hurried back from the window, eager to finish his observations before the coming light show. A trickle of water poured from a pitcher above his head. For the last time that day, Maxwell rubbed a glass rod back and forth across his woolen waistcoat, long since discarded, and held it up close to the steady stream. As he expected, the water bent towards the rod, tugged subtly by an invisible force. A nudge too far and the water reaches the rod itself. This seemingly magical manipulation of the watery stream was the work of static electricity, the attraction of like electrical charges on the rod and in the water itself. No one knew the potential of electromagnetism better than Maxwell. As a child prodigy, he'd spent his teenage years considering the mysteries of mathematics, and had now turned his considerable intellect to understanding the nature of the universe. And so, building on thousands of years of accumulated knowledge, James Clerk Maxwell was the first to visualize the seemingly magical action of non-contact forces as the product of an invisible field, like a three-dimensional web radiating out from its source. Not only that, but Maxwell saw that since electricity could produce magnetism and vice versa, then the fields for those two forces could in essence be combined into one great electromagnetic field. As waves propagated through this three-dimensional web, they carry energy, undiminished from one location to another. Visible light is one such electromagnetic wave. Maxwell's unique perception of electromagnetism as a unification of electricity, magnetism, and optics paved the way for a revolution in our understanding of physics. As he opened the window to his stifling office, he unknowingly let in a breath of fresh understanding for all who followed him, lay down a foundational ace in the cosmological house of cards. His equations allowed electromagnetic waves to be produced and studied in the laboratory, leading to the discovery of radio waves some quarter of a century later, and providing a framework for visualizing the cosmos in an entirely new way, through the action of fields. And so it was that in the early 20th century, Albert Einstein had Maxwell's fields in mind as he rewrote the mathematics for gravity, giving rise to the fabric of space-time, an immense field that is curved and distorted by massive objects like stars, planets, and black holes. Like the endlessly propagating waves of electromagnetism, gravity also acts over cosmic distances, and all is caught in its grip to varying degrees. Although our day-to-day lives are ruled by the gravity of the Earth and the Sun, the force of gravity isn't actually that strong. In order to produce measurable gravitational effects, one must accumulate huge amounts of mass, like the 6 million billion kilograms of the planet Earth. The curvature of space-time produced by a human body, or an apple, is so small as to be almost unmeasurable. Instead, on the smallest scales, the microcosmos is ruled by another, the strong nuclear force. In contrast to the far-felt fields of electromagnetism and gravity, the strong force only extends its reach a minuscule distance, no more than the diameter of a proton. But despite this small sphere of influence, the strong force truly lives up to its name. It is this that binds together quarks to make the protons and neutrons at the heart of every atom. And its residual effects are powerful enough to hold protons together, despite the fundamental repulsion of their like positive charges. Finally, with an even smaller sphere of influence and a potency less than all but gravity, the weak nuclear force may seem barely worth considering. And yet, its effects are ones we rely on for our very existence. The weak force is responsible for changing the flavor of the quarks that make up protons and neutrons, transforming one into another to build or destroy atomic nuclei. These changes, when they occur inside the hearts of stars, fuel the fusion that keeps them burning and stabilizes the assembly of heavy elements. Thus, we ultimately have the diminutive weak force to thank for the life-giving heat from the sun, and for the very building blocks of our planetary home. Between them, the four fundamental forces appear to govern every known phenomenon in the modern universe. Understanding the fields of these four forces has helped modern physicists to grasp, model, and predict the cosmos with spectacular precision. But to answer the question of what these forces really are, and how and when they came to be baked into our early universe, we must step further through the force field into the baffling world of virtual particles. Cornell University nestles close to the southern shore of Cayuga Lake in upstate New York. On late autumn evenings, a gentle breeze blows down towards the lake to blow delicate ripples across the water's surface. In the late 1940s, Richard Feynman, then Associate Professor of Physics at Cornell, sits in quiet contemplation at the shore. He is watching the water dance to the wind's choreography, and he is thinking about quantum electrodynamics. The patterns on the water's surface change from moment to moment, driven by the invisible forces of the wind. Feynman imagines a wind field, much like the electromagnetic fields of his research, radiating out across the lake to create those tiny rippling waves. With enough information, he could imagine reconstructing the wind's field, relating it mathematically to its source atop the hillside. But to truly understand the wind, the large-scale field is not enough. He would need to know about the particles of air that carried the wind's power, how they moved, how they interacted with one another and with the water of the lake. The wind's field relied ultimately on the particles that carried it. Could the electromagnetic field be similarly reduced? Feynman was riding the growing wave of the quantum revolution. For the last 20 years, interrupted somewhat by World War II, theoretical physicists had begun to comprehend the universe on a tiny particulate scale, recognizing that light waves could be quantized into minute parcels of energy known as photons. But as James Clerk Maxwell had shown some 80 years previously, light is also a wave, a manifestation of the electromagnetic field that permeates the universe. How could these two differing viewpoints be reconciled? Feynman provided a mathematical solution in the form of quantum electrodynamics, quantizing the electromagnetic field and defining the interactions of particles that deliver this far-reaching force and its many effects. The messenger of electromagnetism, he determined, was indeed the photon. But photons are not physical, tangible particles like the air molecules that make up the wind. They are virtual messengers, quantized parcels of energy that don't interact with one another, but nevertheless can be exchanged to alter the properties of real matter, producing the different effects of the electromagnetic force. Free photons that are emitted and not exchanged become visible light and other forms of radiation. And bizarrely, according to the strange tenets of quantum dynamics, these virtual photons can briefly pop into and out of existence, even when there is nothing else around, for example inside a true vacuum. Normally, their fleeting existence goes unnoticed, but in 1948, Dutch physicist Hendrik Casimir found that when two mirrors were placed facing each other in a true vacuum, they would be mysteriously attracted to one another. The only agent of force could be these virtual photons. He reasoned that more of the messenger particles could exist outside the mirrored plates than between them, and the resulting pressure difference was enough to force them, ever so slightly, together. The phenomenon is known as the Casimir effect, and it is an elegant demonstration of the energy contained within all vacuums throughout the universe, now and since its creation. Like Maxwell before him, Feynman's new treatment of the electromagnetic force once again revolutionized theoretical physics. Recognizing that one of the fundamental forces of the universe could be so quantized, physicists spent the following decades following in Feynman's theoretical footsteps and seeking the virtual messengers of the other cosmic force fields. The strong force was the next to reveal its secrets, probably owing to its strength, allowing it to be studied in laboratories as soon as sufficiently precise instruments could be built. The study of quantum chromodynamics is therefore concerned with the agents of this powerful, yet limited force. The virtual messenger in this case is the gluon, so named for its ability to glue quarks together to form protons and neutrons. But the message that these gluons carry is more complex than a simple energy exchange of photons. Nevertheless, through theoretical and mathematical attrition, photons and gluons have found a place within a modern framework of particle physics, known as the Standard Model. Under experimental scrutiny, even the weak force, with its tiny reach and feeble powers, has yielded its own virtual messenger particles, called W and Z bosons. And they are different again from gluons and photons. They are massive, with roughly 100 times the mass of an entire proton, making them heavier than entire iron atoms. Compared to photons with zero mass, these massive messengers are confined by their own inertia. To date, only the gravitational force evades quantization. Theoreticians have predicted the existence of a virtual messenger with zero mass, called the graviton, but there are fundamental incompatibilities between the quantum standard model and our other framework for understanding gravity, general relativity. Gravity is 1,000,000 billion times weaker than the weak force, making it impossible to probe with the kind of instruments we can build now, or in the foreseeable future. But even without gravity, the Standard Model has gone a long way to probing the fundamental forces on their smallest scales. And yet, frustratingly, the solutions to these natural puzzles seem far from standard. All of the virtual messengers that we have discovered behave in their own unique ways, and have their own unique properties that render the fundamental forces just that. Fundamental and irreducible. And yet, remarkably and somewhat counterintuitively, physics today is painting a more consolidated picture, in which these irreducible forces are simply facets of a single, unified whole, one which had its origins in the earliest moments of the cosmos.